In this video, we'll be adding and subtracting mixed numbers using two different strategies. One of those strategies will relate back to our regular decimal addition and subtraction. For each of the examples, I've recorded a video that shows how to solve the problem with manipulatives in a way that corresponds with the algorithm. As I play the video, I'll be recording the mathematical written work over on the side, and then I'll point out some of the key things to notice. Here we'll model 2 1/3 minus 2/3. The yellow hexagon is worth 1, and the blue rhombus is 1/3 of a yellow hexagon, so this is 2 1/3. If I want to subtract 2/3, I only have 1/3, so I have a problem. I need to re-envision these yellow hexagons in terms of thirds. So each yellow hexagon is a set of 3 blue rhombuses, or 3/3. It's just like putting it as an improper fraction, so I can get everything in terms of thirds. So I have 3, 6, 7 thirds total here, and I can take away 2/3, which leaves me with 5/3. If I want this as a mixed number, I just regroup and I have 1 and 2/3. So here, it was important that I thought of everything in terms of thirds. I got everything in terms of like-sized parts, so I could take away the 2/3. Next, let's review our traditional subtraction algorithm. So when I have whole numbers, if I had like 452 minus 69, I would write that out by lining up the ones, lining up the tens, lining up the hundreds. So here I want to have like-sized parts, and then I will borrow, trade, regroup, whatever language you want to use to talk about that, but where I am regrouping such that I'm able to subtract. So that should be a familiar algorithm. This works exactly the same way if we were to add on decimal places, so tenths, hundredths, and thousandths. Let's watch this and see. Let's model 2 3/10 minus 7/10. Here we have one small cube represents 1/10, so a rod is 10/10 there. And if I go to take away 7/10, I see that I don't have 7/10, I have 3. So I'll take one of these rods, I'll trade 1, and I'll turn it into 10/10. So now I have like-sized parts, right, all my tenths together, and I have 13 of them, so I'll be able to take 7 away, and I'm left with 1 and 6/10. So just like with whole number subtraction here, we're lining up our tenths, lining up our ones, and then we're regrouping, we're ungrouping, we're taking 1, 1, make it 10/10, so I have 13/10, and then I can subtract. Now we'll do a similar thing with mixed numbers. Now when I take 2 1/3 minus 2/3, I'm going to think of my ones separately from the fractional part of my number. So I have 2 ones and then a third. So to take away 2/3, I will make one of those ones into 3/3. I'll trade it over to the side with the fractions, so with the fractional part, and I'll have 4/3, take away 2/3, and I'm left with 1 and 2/3. So here again, I lined up my whole numbers, my ones, I lined up the fractional part, and then I took 1, 1, turned it into 3/3, which gave me a total of 4/3 on this side, and I could simply take away my 2/3 to get 1 and 2/3. So let's do the same thing with addition. We'll start with our traditional improper fraction addition strategy. Here we have 1 1/2 plus 1 2/3. With our traditional improper fraction algorithm approach, we'll start by turning each number into an improper fraction. So 1 1/2 becomes 3/2, and 1 2/3 becomes 1 2/3. 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 1 2/3 becomes 5/3. But when I go to add these two numbers together, I don't have like-sized parts. So I'm going to have to further partition the whole. This time I'm going to work with 1/6. So I'll look at my green triangles here, and I can see that my first number in terms of 1/6 becomes 9/6 right there. 1½ is 9/6, and 1 2/3 is going to be the same as 10/6. So when I'm adding, once I have like-sized parts, then I am just adding together all of those 6, all of those like-sized parts. So 9/6 and 10/6 gives me 19/6. And if I want to put this back as a mixed number, I'm going to have to reform my wholes. I'll get 1, 2, 3 wholes, and then 1/6 left over. So here, I went to improper fractions, but I needed like-sized parts, so I got a common denominator. Common denominator, the denominator tells me the size of the parts. Then I could just count up the total number of parts, 19, each worth 1/6 of a whole, which I can rewrite as equivalent to 3 1/6. So now let's do this the other way. Let's think about adding 1½ and 1 2/3 in a different way. I'm going to think about this like I do my decimal numbers, where I line up like-sized parts. So my 1s here, those are like-sized parts. I line them up. Together we have 2 1s. With my fractional parts, I line those up, but I don't have like-sized parts. So now I'm going to turn them into 6. I'll use my green triangles. So my 2/3 becomes 4/6. My 1/2 becomes 3/6. Once I have my like-sized parts, I can just add them. I have my 7/6 right there. Or I regroup, and then I can trade 6/6 for, I can trade 6/6 for 1, and I end up with 3 1/6. So here again, it's key that I lined up vertically like-sized parts, because when I add, I have to be adding like-sized parts. I could add my whole numbers, but here I needed to get a common denominator, the 6, so that they were like-sized parts. I had 7/6, and then I could do some work to get this back to a mixed number as opposed to a mixed number that included an improper fraction. So let's take this up a notch and let's do an extreme example. Let's do 17 3/8 minus 4 5/6. So sometimes one method is just better than the other one. Here the inferior method would be the improper fraction method, because the numbers are going to get very large and unwieldy, and I'm going to do a whole lot of work here that I could avoid. When I turn these into improper fractions, right away, 17 times 8 plus 3 over 8 minus 4 times 6 plus 5 over 6. Already, 17 times 8, I'm going to have to do that calculation. Then when I get the common denominator, those numerators are going to get really, really large and harder to work with. So let's go with our other strategy here. I'm going to line up my 1s together, line up my fractional parts together, and then I'm going to say, well, my fractional parts need a common denominator. The common denominator is 24. So I'm going to end up with 9/24, and I'm going to end up with 20/24. When I go to subtract, I have a problem, 9 minus 20. So I take 1 from the 1s, and I rewrite it as 24/24. That's going to give me 33/24. 33 minus 20 is 13/24. In the 1s place, 6 minus 4 is 2, and so I have 12 13/24. That ended up being much easier than improper fractions.